This is the experimental demonstration for MAE535 at NC State. Today's demo of an applied electromagnetic device will be an electromagnetic powered vehicle. The goal of this project is to demonstrate how current applied to a solenoid can be used to create a uniform magnetic field along the axis of the solenoid in accordance with both Biot-Savart's law and Ampere's law. The vehicle is powered by the resulting magnetic field acting on permanent magnets. The design parameters of the electromagnet are varied to determine the effects of the strength of the resulting magnetic field on the velocity of the vehicle. It is experimentally shown that the stronger the magnetic field, the higher the velocity of the vehicle. Both Biot-Savart's law and Ampere's law are used to calculate the magnetic field intensity near a current-carrying conductor. Each law can be applied to determine the magnetic field intensity of a solenoid due to an applied current. A solenoid creates a uniform magnetic field in the direction of the solenoid, since all radial components of the magnetic field will cancel. A discrete Biot-Savart summation would be impractical for a solenoid with a large number of turns, so instead an integration approach was used. Ampere's law provides another approach to calculating the magnetic field intensity by evaluating the closed contour integral of the current density through the surface. While an application of Ampere's law is only useful for certain geometries, the magnetic field intensity of a solenoid can be approximated. The drive design of the electromagnetic vehicle used in this demonstration is a variation of the simple electromagnetic motor. However, instead of the force being generated by a current moving through a wire loop, the torque is created instead from the magnetic field surrounding a permanent magnet interacting with the magnetic field produced by the solenoid. Similar to the electromagnetic motor design, a commutator must be used to terminate the creation of the magnetic field from the solenoid as the permanent magnet aligns with the magnetic field. In this demonstration, different parameters will be changed to attempt to produce different strength magnetic field intensities from the solenoid. 3 different solenoids were tested, each a different turn density: 91 turns, 182 turns, 363 turns. The vehicle at each different magnetic field variation was timed, covering a predetermined distance of 10 feet or 3 meters to calculate an average velocity. Using Biot-Savart's law and Ampere's law to estimate the strength of the generated magnetic field based on turn density, it is hypothesized that a stronger magnetic field will produce a faster velocity of the vehicle. The vehicle is powered by a 9-volt battery. The positive end of the 9-volt battery is connected to one end of the 28-gauge copper solenoid. The other end is connected to the metal armature made out of coat hanger. It passes through the permanent magnets to the commutator, which is spray painted. Every 90 degrees, it is sanded smooth to allow contact between the armature and the bristles to connect to the circuit. The solenoid is connected to the bottom of the vehicle using zip ties, so the solenoid does not come into contact with a permanent magnet during operation. The vehicle was tested on an indoor, straight, flat course of 10 feet or 3 meters. At 91 turns, the magnetic field produced from the solenoid was not strong enough to move the vehicle. At 182 turns, after 3 runs, the average time was 10 seconds for 10 feet, or 0.3 meters per second. At 363 turns, after 3 runs, the average time was 8 seconds for 10 feet, or a velocity of 0.375 meters per second. And now for a view of the runs.